I need your help. I'm putting together this video because I need your help in order to put together a presentation for the government. I want to go to the government and say, hey, listen guys, on your plan of attack for the next decade, and the next couple of decades, we are still going to be burning coal as part of our power requirements. And I know that we're putting in wind farms and we're putting in solar and we're looking at hydro schemes, but we're still burning coal, and that's the last thing that the environment needs. Right now we're all at home with being bound because of the coronavirus. Before that we had the summer heat, the bushfires. Before that we were all concentrating on climate change and what we can do for climate change, but we've all forgotten about that now because of the virus. What I want to do is I want to go back to the environment and something we as Victorians and we as Melburnians can do. And I want to take you through something that I think is important and it's very precious to me. And I'm just going to do this on my computer screen. It's a little bit old school, but here we go. Okay, clearly a map of Australia. And here we are down in Victoria, and particularly Melbourne. You can see this black dot here is the bay. Where we get our power from at the moment is over here in Traralgon. There is the big giant open cut coal mines. There's the Bellarine power station, and that's where we get all our electricity from. We're burning coal. We're still in the dark ages of burning coal for all of our power requirements. Out here in Bass Strait, we've got gas fields. We also burn gas fields. We mine the gas, we ship that overseas. We have up here a bit of a small power station coming off Eildon, and the governments are now looking at the Snowy Hydro scheme. And in proportion to Melbourne, here's Jindabyne and Eucubbene. This is the Eucubbene Dam up here in New South Wales. Canberra's somewhere in the middle here. There's Canberra up here. And the Snowy Hydro scheme is a very, very long way away from Melbourne. To get that electricity here, that's a big job. That's hard work. We have we're burning our coal, which is quite conveniently nowhere where we get affected because of all the winds. The winds blow the smoke the other way, and as Melburnians, that's good for us. We can charge our electric cars up at the power point without having to worry about seeing any smog and pollution that you get from burning coal all the time. And these things run 24 hours a day, okay? We don't have any mechanism of stored power. And except for this bay contains about 25 cubic kilometers of water. And it empties out at the heads here. Those of us who live around the bay are familiar with the heads. We've got the Mornington Peninsula on this side. Here's Portsea and Point Nepean. We have Queenscliff over here and Point Lonsdale on this side here. And we have, you can almost see the flow of water that comes out through the heads here. And we have tides. We have tides every 6 hours. So the tide will come in and go out, come in and go out. It does it 4 times a day. And so we have this huge amount of water coming through the heads 4 times a day. And we have not captured, and I don't understand why the government and the energy minister is not capturing this amount of energy. It's free energy. It's an enormous amount of energy. And we've got to do it. We've got to move away from coal. Absolute number one, we've got to stop burning coal. We've got to be at the front foot of leading the world with clean energy. Now, putting wind in, that's great. Putting solar in, that's great. But when it's not sunny here in Melbourne, not sunny here in Victoria, that's a problem because we're not getting any energy. When the wind is not blowing, we're not getting any energy. But 4 times a day, this tide is coming in and out. Okay, and so I want to show you a model of something that I've been working on, a design that I've been working on. So here we are, here's Port Phillip Bay. It's about 20 meters in average depth in the middle here. And as we come down here, we have some really, really shallow areas where it's only about a half a metre, it's only a couple of metres through here. And then you can see this big white channel along here, that is where the ships come out of the bay. At the end of that shipping channel is a big deep trench running through here. And on the Point Lonsdale side, it goes from about 60 metres of depth, and there's a sheer cliff that runs around this side of it like so. And it goes from about 60 metres of depth up to about 6 metres in depth in a very short space. So very big cliff face. Now this used to be a river. Once upon a time, before the bay was filled with water, this was about 5,000 years ago, this was all land. And this is the bottom of a river. And it came out and then exited the heads like so. And eventually joined up with the ocean. But 5,000 years ago, this was all land and we could actually walk to Tasmania. And as a result of it doing this, we're left with this big trench. And those of us who know this area, it's a very dangerous piece of water because of the currents that come in and out, and of course our weather from Melbourne is predominantly southwesterlies. But I want to show you what I'm working on in terms of just occupying this tiny little bit of stretch here. It's about 1 kilometre long. You can see here the shipping channels. This is where the ships go. This is the entrance. And I just want to show you what it is that what I'm proposing in this space here, because I think this is really important. There's a couple of black lines through here, that they're ships coming through the shipping channel, and you can also see another line in here which represents, it's got a couple of markers on the end. That is 1 kilometre. Okay, so I'm just talking about 1 kilometre's worth of space. As we fly in like this, you'll see what I'm talking about. The ships are sitting over here in their shipping lane, and the energy farm, the tidal farm, I want to put into this deep trench here. And the reason why I want to put it into the deep trench is because that's where you get the hardest and fastest flowing water. If I take you back for a second to looking at how flow rates work in streams, you always get the maximum flow away from the sides and away from the bottom. There's too much friction along the bottom and along the sides. And so you'll always get the fastest flow in the middle of the deepest part, and when it goes around corners, the water will try and push out, because it's just the sheer weight of it, push out to the outer edge, like so. And this is well known. It's understanding flows through river and tidal stream effects. This is very well known. It's not new. So here is my kilometre. We have inside of that kilometre this deep trench, tidal farm towers holding various turbines, just to give you an example of what it is that I'm trying to convey. Here is a working barge. You can get a bit of a sense of scale, and that's the barge that we're going to be using to do the maintenance on these structures. This first one is a giant ring tidal generator, and you'll see it in things like here. And look, there are lots of generators available. The most common one looks like this. It looks like a wind farm generator. It has some blades on it. It's got a generator. It obviously needs to sit on the floor of the space. In our case at Port Phillip Heads, we're now 60 metres deep, which is not great. And we don't want that at the bottom because that's where the least amount of flow is. If you have a look at this structure just here, it's hard to see it, but this is what happens to structures underwater. They get fouled up with marine life. But these are all conceptual ideas, and they're not really suitable for every type of environment. And very rarely do you ever have a beautiful, nice flat bottom and everything is hunky-dory and perfect. So this represents a colossal ring generator. It is a massive piece. Now I'm not sure whether you can actually see it, but down the bottom here is a person standing just here. That's how big this generator is in order to capture the flow. You can see the turbines around there. It has this donut on the inner ring, which I'll explain in a minute, and this massive cowling on the outside here. And the way it looks, if we look at it in half, and I just zoom in on where this guy is at the moment, we have what really just looks like is an aeroplane wing. And what we're trying to do is we're trying to speed up water over this curve. And so where the blade or the turbine is, we want to get the fastest speed through here. Now we don't necessarily need this laminar flow like a wing does, where we're trying to create lift. What we're trying to create is just speed. So we don't need all of this structure, but you get an idea of just how difficult this would be. This is 40 meters in height, 39 meters in height, this thing. It is enormous, and it's round and it's complex. So what I did is I split that into two similar sized turbines. They're about 200, and the combination surface area is about 230 square meters. Same principle, same wing shape, same view of trying to accelerate water through. But these need to turn with all of the different kind of currents and eddies that happen with water flow. And if I just show you, when we look at flows around cylinders, a lot of research has been done on this. All the information is out there. And it's not how, this is what's known as computational fluid dynamics, where we put an object in, we say that this is water at a certain speed, and we can see what happens to the water and the effects of it afterwards. Here's some flows. You get these eddies that come off the backside of a cylinder, and the cylinder is something that's going to be our structure, and we know what happens with these eddies further down. There's nothing new about this formula. The mathematicians have been working this out for a very long time. This is these donuts around these blades is a technology where we try to create cylindrical flow around here, because we want the cylindrical flow, because we know that just at this point, just after the top of the cylinder, that is where we get the maximum amount of water flowing. These are not necessary. These are a really complex design. So this is what's known as a horizontal axis water turbine. And it's no different to the wind turbines that you see on farms out in the countryside. These must point directly into the current at all times, so you really need a mechanism for this kind of blade to turn into the oncoming stream at all times. And as I just showed you what happens around eddying around these objects, this becomes really, really challenging in the sense of water, and particularly when water is moving around a deep channel like so. You can see some other turbines here. Now these are my design, and I want to create what's known as a vertical axis water turbine. And it's based on the principle of Sylvanus, but it's just slightly different. I like the idea of creating generators that are outside of the water. I do not like the technology where people are putting concepts where they're putting the generators underwater. I think that's madness. From an access point of view, from a maintenance point of view, from the ability to swap them out, this is really easy, and I'll come back to that in a minute. What happens with this vertical axis water turbine, it doesn't matter which direction the water hits these things, they still have the ability to turn around. It doesn't matter where the currents are and what the day is doing, because it changes all the time. So let's have a look at one of these turbines as they're moving around. Now, water moves at different speeds depending on the height and proximity to surfaces and what's going, the wind and the waves and the floor and the time of day, and all sorts of things influence tide. And particularly when we're in a trench, there's eddying, there's all sorts of things going on down here. We have a vertical axis set of blades. and they each are put into shafts that go up to the top. So each of these turbines is actually connected to their own generator sitting at the top. And this means that we can one can be ruled out. If we have a problem with one of the generators, then we can disable the actual turbine blades, or we can go and do the repair work or maintenance to the generator, so on and so on. These blades are actually made out of recycled plastic. We don't need a huge deal of strength in here. They are more like an aircraft blade than anything, and what you'll see, and I'll show you another example in a second, is that you have one zone where the water is always coming in. It doesn't matter which way I stand on here, there will always be water coming in on one side and one side not. It's a design that's not particularly efficient. It's actually not as efficient as a blade where you've always got positive lift. This side actually produces a lot of drag, but because of the design, I've actually got the power that I'm looking for is inside here. It's not actually related to the outside one. So I'm deflecting a lot of the drag away from the inside turbines. These are connected to a shaft, which then goes up the inside and connects to the generators. So this becomes a farm. This valley becomes a bit of a farm, and so I've got some of the examples of my turbines, and then I've got some other examples in here. So here's the donut, the shroud that goes around a horizontal axis turbine. And I think it's really important. A lot of concepts have the generators underwater, which I personally think is a really bad idea. I like to see them above the water. And as you can see, as we come up here, these are staggered. We've got them in a staggered position because we're trying to get full flow back again by the time it goes from through one set of turbines and then through the next set of turbines, like so. But this is the stretch that I think is really, really important. It is outside of the shipping channel. It's 60 meters deep, which poses massive, massive problems in itself. But it's a really, really powerful stretch of water to put these things in. So here's the working platform. It can come and access the generator zones. People can get in and out, and these can be safely lit up, they can be safely marked at night time for all boating, not during the daytime as well. And a platform can be made safe so that during the weather when it's suitable, people can get on and service the pieces of machinery, and they can be swapped out if need be, either craned out or wheeled out. And as far as the cabling goes, the electrical cables can actually run down the inside of the towers and then along the ground and up towards Queenscliff or back over towards the Mornington Peninsula side. I'll show you a really good spot for that at the moment. During the construction phase, we will need to put in a temporary structure that sits up on his legs and sits in that shallow bit of water. So it's only about 6 meters deep here, but there's obviously going to be a need to bring in and build and construct these things and somewhere secure for boats to be able to tie up and whatnot. So this is looking back at the tidal farm from the Point Lonsdale side, and if we just come down and stand on the pier here, that is about what you're going to see. You're just going to see the tops of where the generators are, which they're there, you just can't see much. So let's have a look at the construction of one of these things. So it's generator tower on the top and the turbines down below. And this is about 60 meters deep. That needs to be obviously very strong, and the central tower is fixed. It doesn't rotate or do anything like so. And you can see that it's made up of a series of, it's got these big rings around it. And inside these rings are the actual turbines, and they get built up like so. And then eventually the turbine construction is finished. These come in halves. These are really easy to put together. And then eventually on top comes the platform that houses all of the generators. And that is my proposal. That is what I think, this is what we should be doing as a state. Looking at the power potential, the energy potential that comes out of our Port Phillip Bay at the heads. And I want to put together a design and a package that I can take to the government and say, hey, this is what this is going to cost. This is what we should be doing. If you haven't got a plan right now to stop burning coal, here's a solution. And the solution is that this tide comes in 4 times a day. Now we are going to need stored energy. So this power only, it isn't running 24/7. It's only running a number of hours during the day. And so it needs to be put into some sort of storage bank back on land. And then from that storage, fed back into the grid. And I'll show you a little spot which I think personally is a terrific spot. Of course there's going to be conjecture and there's going to be bureaucracy and there's going to be all sorts of things, but if people can get away from looking after themselves and thinking that this is going to spoil their view, well, think about where we are with climate change right now, and our contribution, burning all of that coal and that gas, is not helping. And if everyone wants to move across to electric cars, well, that's not helping either, because of all of that electricity just comes from burning more coal. So looking at Google Maps here, you can see the bay. It's an odd shaped thing. Geelong's over here, indented heads in the middle. And we look at Portsea and Point Lonsdale here. There's a great opportunity for the manufacture and the construction of all of this thing to be done by locals living in this area. There's a great facility at Queenscliff for boats to be able to come in and out. That is a really difficult harbour to get in. You can see these speedboats here possibly going against the current there. The current there is, those boats are not going fast. The current that comes out of this thing is astronomical. That's Swan Bay in here. It empties out here and it empties out further up here. So here's where we're talking of the kilometre of tidal farm going into just here at Victory Bight. You can see the shallows through here, and I want to use this piece of land that comes through here, Queenscliff Natural Reserve, Queenscliff Nature Reserve, and you can see a little block of land just there. And if I go and stand on the road here, you'll see up here there's infrastructure in place ready to connect to the grid. Coming back out of here, if we have a look up the road a bit, you'll see over here, this is the Bellarine Highway, and that Bellarine Highway carries all the power lines all the way to Geelong, straight through there. And there's loads of land and availability to put in a little substation somewhere. I'm not suggesting that it gets done in Queenscliff, but perhaps further back in these rural spots here. Maybe someone would like to sell us a little piece of land for the ability to go and put a substation in. So I think that's very doable right there. On the other side of the bay we have Point Nepean National Park, a very sensitive area through here. More challenging to get a line in somewhere. But there are means of being able to get in here. Those kind of things can be worked out. There are roads. There's ability to go and put in underground cabling underneath these roads, or alongside the roads at the very least. Through here or underneath the pathways. That's not the end of the world. That can be done. There's Pierce Barracks just here. Possibly a good location to bring a cable across and out, and then just follow the natural paths and out. So this is what I want your help with. I want to be able to put together a cool kick-ass presentation to the government, a good bit of video, a good bit of fact, you know, let's tell them how many megawatts we can put into the grid using this tidal energy. Let's show them the technology that we want to put forward. Let's say, okay, here's our vertical turbine. The vertical turbine 4 times a day is going to produce X number of kilowatts. And the system's going to cost this much, it's going to cost X number of years to pay back, but what we're doing by putting that energy out, this is how much carbon dioxide we are not burning from coal. So the coal power stations have got to go, and we need new resources. We need new sources of clean energy. We've got a massive big ocean out there. Wave power is a little way away, but this mechanism inside the heads here, there is just so much potential to be able to capture that energy, and I want your help to be able to do it. As you know, I've been working on a number of conceptual designs for the ability to capture energy through water movement, and there's loads of them out there on the market, and all sorts of ideas and concepts. But very few actually make it to reality. Just the working in water, the cost of them, and some of it's just the difficulty of actually being able to get them into place. And certainly down at the heads, it's 60 meters deep. It's some really rough water and a challenging spot to work on. But if it can be done, if it can be achieved, then that's a good thing. That's a good thing because it means we can stop burning coal, or we can reduce the burning of coal. Let me show you a little bit about what it is that I'm working on. So as you know, I've come up with a whole bunch of kooky ideas and looking at different ways of being able to achieve just maximum effort and flow and force into this turbine arrangement. But let me just show you what I finally settled on. So it is really a 2-blade turbine. It's made up of 3 rings and sits on a big plate here, and it's got the big giant support tower in the middle there, and it does actually have space between the blades and the tower for water to be able to flow through. The idea is that on one side you have all of your water entry, and on the other side it's blocked out, and it doesn't matter which way, any sort of subtle flow of water, the water will always come in onto one side. So this is the Savonius concept. And the problem with it is that if this is revolving, there's a huge amount of resistance and drag on this side and not enough to keep pushing it around on this side. So in this case here, the outer ring is actually just a diffuser. We're trying to funnel water into the turbines, and we're actually trying to block water. We're trying to block water in a way that helps with the actual exit. The water comes on here, you can see the aerofoil shapes here, and then it actually gets pushed out because of the actual curvature on the outside of the blade. So let's have a quick look at how this may work. The water gets funneled in here, it goes over these wing-like structures, it creates a lift, it starts to turn the outer ring. The outer ring builds up a little bit of speed and creates a bit of a vortex in here. There's still water moving through the center of this thing, goes over these wings at the front here, it pushes the back side of the wings on the back side here, so we're getting kind of a double effort there. And then on the far side where it exits, as the blades go around, they spin the water outwards. So we have water coming in, it moves through like so, and then gets spat out like that. Now, this is all just made out of recycled plastic. All it needs to be is something like a high density polyethylene. Now, high density polyethylene is actually lighter than water, so in terms of its weight, the structural weight of these things, they're actually buoyant. We do need to put in some infrastructure in place, some bearings and things like that, but the fact that they sit on a bearing plate underneath here, but there's very little weight on them. We have the means of adjusting as well. If we wanted to adjust our vents, we can adjust them. This is a 2-ring system where this outer plate can actually swivel past each other like that, and by doing so it can actually change the angle of the inlets, and so we can achieve a better efficiency. It's most likely we can do the same technology with these guys as well, but it's most likely that they won't. They will just get fixed to a certain point and never really need to be moved again. And the CFD will tell us, once we work out our maximum efficiencies, will tell us what those angles are going to be. So as we've just had a look at, we've always got a side that is always open on one side and always blocked on the other side. It doesn't matter which way the water is coming in. As the water enters, it flows over these aerofoil shapes, creating a lift. At some point, depending on which way the water is going to come in, there's going to be a point where the aerofoil works, but then there's a point where the aerofoil doesn't work. And then it moves from just being lifted to then being pushed from beneath. So these outer blades that are drawing water in like so will end up with a pushing effect. And then of course the water flows inwards and flows beyond these ones and flows onto the inner side. And what I'm expecting is that this is actually creating its own vortex effect in the middle, as well as the water that's flowing through the structure. And of course, it gets spat out the other side here. It all gets flicked outwards on this side here. What drives this thing is on the sides of these rings, which drive around on bearings, are these bevel gears. So these bevel gears connect to the inner bevel, and that's a drive shaft here. And that drive shaft goes inside the tower like so, also onto another bevel gear, and then all the energy and turning motion is taken up to the generators. And there's 8 of these turbines in place, and so there's going to be 8 shafts and 8 generators sitting at the top. They obviously don't sit at the top like this, they actually sit underneath. And they are connected to the top plate. I just haven't drawn this one in just for clarity, and I haven't drawn the top plate on this one just for clarity as well. So there you go, there's an introduction to a concept which is really looking at a tailor-made solution for the 60-metre channel that sits at the Port Phillip heads. It's 1 kilometre long. And we can fill it up with a number of different of these vertical access towers. Other spots that this could be applicable for would be Western Port Bay as well. And alongside there's a shipping channel also in Western Port that just hooks around French Island, and also on the other side of Port Phillip Island there's some really good tidal flows there as well that this kind of technology can be put into. Where it differs, I suppose, well, obviously there's the whole level of engineering technicality that's required, that's a given. But the actual structural elements itself, I think can be made out of a lightweight recyclable plastic, which is the angle that I want to take, because I think that's important. I think there's an opportunity to go to Victorians and say, hey, listen, why don't we come up with a scheme where everyone collects their milk bottles. The milk bottles are made out of high density polyethylene. We'll collect everyone's milk bottles, we'll mash them up, create new high density polyethylene boards, and then we shape the boards to what you're seeing in here. And it's pretty simple. The shaping of polyethylene is very simple, very hard to glue it, but we have an internal structure. We can screw the shapes together, we can mould up nose pieces and leading edges and those kind of things. And And it floats if it gets damaged. Well, then it floats out to sea. But to make it all out of steel, that's very hard, very heavy. There's corrosion, no corrosion in plastics, and it's a good opportunity to start recycling and get everyone in Victoria on board. Why not? This is something for our future and our kids' future and generations beyond. So this is probably a really easy thing to achieve. It's not that hard to collect milk bottles and come up with a collection system. That's where I'm at. So I really need help with with putting all this together in a presentation. So maybe videos. I need a professional presenter, someone who can speak without muttering and mumbling and saying all the time. I need someone who's definitely better looking than me. I need someone who can convey the message. I need script writers. I need who have knowledge and experience of actually presenting to the government for grants. I need engineers who can come up with data. I need people who in computational fluid dynamics who can run these things. Engineers who can work in 3D CAD. There's a whole bunch of people I need before I can actually make a presentation to the government, and then we can make a presentation to the government, and they say, okay, we'll give you some money. We like it. How much is it going to cost? You go through the bureaucracy. And the thing that I'd hate to lose out to the big energy companies who can charge an absolute fortune for this kind of stuff. You know what? I'd really like to see it be done sort of fairly, where the money goes into Victorians and locals, and it's manufactured locally and designed and produced locally, and it becomes our thing as opposed to outsourcing it to somewhere overseas. And it just takes a bit of leadership and direction and knowledge and know-how, and that we can gain from experts. But it would be really nice if we could just achieve this in Victoria at home here. I would hate to just outsource something like this to China or somewhere where it's just all about cheap labour. I really hate that idea. I hate the idea of people working for really little money for some energy giant's gain and their shareholders' gain. It just goes against my grain. But so maybe help me with getting over that. I don't know.